Hi there and welcome to another video from HEGARTYMATHS, a Core 4 Maths A-Level video, and in this video we're dealing with the topic of the trapezium rule within the integration chapter. As always, for more help with your math studies, do check out YouTube, Twitter or Google+. In this tutorial we're talking about the integration in chapter 6 and we're going to cover the trapezium rule. As always, it's applicable to Edexcel Core 4, but should be also applicable to most other core maths modules. Looking at the syllabus, what we need to do and what we're going to cover off here is the numerical integration of functions, and we're going to use the application of the trapezium rule to functions covered in Core 3 and Core 4, use increasing number of trapezia to improve accuracy, and estimate the error will be required. It does say here that questions will not require more than 3 iterations, okay, and Simpson's rule is not required. So it's a discrete one-off topic here that we can cover off in one video. Okay, let's talk about the big picture here and what this topic is all about. First of all, let's consider the area under a curve. Here we have a curve, y is equal to some function of x, and we want to work out the area between x is a and x is equal to b. Now, this area we would usually write as the integral from x is a to x is b of y with respect to x, or sometimes we would write this as the area is equal to the integral between x is a and x is b f of x dx. Okay, and that would give us this area here, which we will label area, and it will give us the exact area. Integration is a technique to find the area under the curve between two x values, for example. Now, suppose we were not able to integrate this function, this y function or f of x. Suppose we didn't know the integral and we were using estimates to try and find this area. The first thing you might decide to do is you might say, well, instead of integrating using calculus, what I could do is I could split the I could split the interval between x is a and x is b up into, let's say, 4 rectangles or more, and I could work out the area of those rectangles. It's easy to work out the area of a rectangle, and if I add them up, it's an approximation to the area that I'm looking for. Okay, so that is one way to try and approximate these. Obviously, the more rectangles you have, the smaller the error and the closer your answer would be to the real integral or area. However, rather than using rectangles, suppose we use trapezia. Here's a trapezia. It's got 2 parallel sides, and then the other pair of sides is not parallel. It's a quadrilateral with one pair of parallel sides only, not 2 pairs, 1 pair of parallel sides. So instead of using rectangles, if we use trapezia, as you can see here, you can see that the approximation for the area gets far better. Okay, so this is what this topic is about. It's approximating the area under the curve using a trapezia. Okay, and this is how we're going to do it. I'm going to derive the formula for you, although you don't need the derivation, but just for background. Now, supposing we wanted, suppose what we did is we're integrating, or we're finding the area even between x is a and x is b. Suppose we divided this up into intervals and equal intervals. Suppose we said let h equals let's say b minus a over n. So for example, if we said if we let n equal the number of trapezia, or sometimes we call these strips, the number of strips, then what we would do is we would divide this width, b minus a, into those number of strips. So it would tell us how wide each one would have to be. So for example, say, I don't know, b was equal to 6 and a was equal to 2, and we wanted n is equal to 4. Our height, this distance here, this would be our height, would be equal to 6 take away 2 over 4, which would be 1. So each of these lengths would be 1. Okay, so suppose we did that, okay, and suppose also we called the original point, x equals a, we called that x0, we called the next point along h along x1, the next one along x2, the next one along x3, and the next one along x4, which was the same as b. Suppose also that when we worked out f of x0, it gave us y0. When we worked out f of x1, it gave us y1, this height I mean. When we worked out f of x2, it gave us the height y2, similarly y3, and lastly y4. Okay, so suppose we had done all that there. Now, what is the general formula of one trapezium? Suppose we had a trapezium that looked like this. And these are what all these look like here. This side had height A, this side had height B, and the distance between these was h. What's the area of a trapezium? Well, the area of a trapezium is a half the sum of the parallel sides A plus B multiplied by their distance apart h. So let's give it a go to work out these trapezia. Let's call this trapezia 1, 2, 3, and 4. So the integral of y dx between a and b is approximately, it's not exactly, it's approximately the sum of 1, 2, 3, and 4. Now, what is the area of this trapezium? Well, the height, it's a half. The sum of the two heights, so y0 plus y1, plus the distance between them, which we've said is h, plus this one, which is a half, y1 plus y2, and the distance between them, which is h, plus this one, a half, y2 plus y3, multiplied by the distance between them, which we've called h, and plus a half, y3 plus y4, multiplied by the distance between them, which is h. Now suppose we added these up. Let's factorize out a half h, because a half h is in all of them. Let's take out a half h. So I'm taking out here this half, this h, this half, this h, this half, this h, and this half, and this h. I'm factoring that outside. We would have y0 plus y1 plus y1 plus y2 plus y2 plus y3 plus y3 plus y4. Okay? And what we would get from that if we combine, we'd have a half h. Now we would have a lot of these things collect up. We've got a y1 there, another y1. We've got a y2 here, another y2. And we've got a y3 here and another y3. So what we would have is we would have a y0 plus y4, let's say, plus we would have two lots of y1 plus y2 plus y3. Okay? And that would be an approximation for the area under this curve here. Now obviously, if we split into not 4 strips but n strips, the same formula would apply, and I'm just going to write that formula. This integral here would be a half h y0 plus yn plus 2 lots of y1 plus y2 dot 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 to yn minus 1. Okay, where h is b minus a over n. H is the width of each strip, so it's the total width of the gap divided by how many strips you've got. Okay, so that's where this formula comes from, which is given to you in the formula booklet. And let's have a go at applying it now. So here's the formula that's given to you in the formula booklet here, and they say again this integral is a half h, the first ordinate y0 plus the last ordinate plus twice all the y ordinates in between, where h is equal to this. Okay, so let's have a go at trying a question. Here's the first question. Use the trapezium rule with n strips to estimate the following. The integral between 0 and 3 ln of 1 plus x squared dx, where n is 6. Now for these trapezium rule questions, I always want you to draw a table. The only way to do this properly is to draw a table. Before we do that, let's work out our h. H is equal to b minus a over n. So in this case, our h is equal to 3, take away 0, the b minus a, over n, which is 6, so h is equal to 0.5. Okay, this is important for our table. So, this is our table here. These are going to be our x values, these are going to be our y values, and this is going to be the trapezium rule that we apply. Okay, so our first x value is 0, and then we're going up in half, so the next one's 0.5, the next one's 1.0, the next one's 1.5, 2.0, 2.5, and 3.0. Okay? And I'm going to call this x0 equals x1 equals x2 equals x3 equals x4 equals x5 equals and x6 equals. And I'm going to work out y1, y2, y3, sorry, this is y0, y1, y2, y3, y4, y5, and y6. I'm going to work out each of these. And how I work these out is I put x0 into the function. So it would be ln of 1 plus 0 squared, which would be ln 1, which is 0. If I put a half in, it would be ln of 1 plus 0.5 squared, and ln 1 plus, so I'm going to calculate that when it's 0.5. So it would be ln 5 over 4. Leave it fully, don't try and decimalize it. The next one would be ln 2. I'm going to put 1 in. The next one would be ln 13 over 4. The next one would be ln 5. The next one would be ln 29 over 4. And the last one would be ln 10. Now it's important at this stage not to decimalize these, as the answer will get more wrong. Now in the trapezium rule, we need y0 and we need yn, the last one. So we're going to firstly just write out that we're going to have 0, y0, and we're going to have y6 is equal to ln 10. Now all the others we need to double. So we're going to double each of these. So the next one will be 2 ln 5 over 4. The next one will be 2 ln 2. The next one will be 2 ln 13 over 4. The next one will be 2 ln 5. And the last one will be 2 ln 29 over 4. Okay? Right. So now what we're going to do is, in the trapezium rule, we add up these numbers. So we're going to total this column up here. So we type all of these in our calculator. So we add 0 plus 2 ln 5 over 4 plus 2 ln 2 plus 2 ln 13 over 4 plus 2 ln 5 plus 2 ln 29 over 4, and then we say plus ln 10. And we get our calculator to work that out, and at this stage the total adds up to 13.67335531. Keep it like that until you round at the end. So we're going to estimate this. The last thing we need to do is we need to multiply by half h. So we're going to take this, the area is therefore a half multiplied by a half multiplied by 13.67335531. And our approximation for the area is 3.442 units squared to 3 significant figures. And that is our answer for that question, 3.42 units squared. So with this, the easiest way to do trapezium, rather than try and substitute in a mess, Step 1, work out your h, which is your b minus a over the number of strips. Step 2, write down your x0 to xn. Next step, step 3, is to work out your y0 to yn by substituting your x0 into your function, okay, into this function over here. Do not round as yet, so keep it as a an exact value. Last column is to keep the y0 and the yn and double all the ones in between. Next step, add that, and lastly multiply by half h, and we're done on that. So the answer was 3.42 units squared. Okay, let's have a go at another example. Here's example 2, in which we're factoring in using more strips to get a more accurate estimate, and we're working out a percentage error. Okay, so firstly, it asks us for part A to find the exact value of this integral. So for part A here, we're working out the integral between 0 and pi by 3 of sec x dx. Now, sec is one of the integrals that's given in your formula booklet. You're trying to work out this integral, you look at the formula booklet, and it's equal to, when you integrate that, you get ln sec x plus tan x, ln the modulus of sec x plus tan x, and it's between 0 and pi by 3. So what you do is you put pi by 3 in, and then you subtract the answer when you put 0 in. So it's ln sec of pi by 3 plus tan of pi by 3. Okay, subtract ln sec of 0 plus tan of 0. Okay, let's try and work each bit out. Now, sec of pi by 3 is 1 over cos pi by 3. Okay, and cos pi by 3 is a half, so sec pi by 3 must be 2. So this is ln of 2, and tan pi by 3 is actually equal to root 3. So we've got ln of 2 plus root 3, subtract, cos of 0 is 1, so sec of 0 is 1 over 1, which is 1. Tan 0 is 0, so we're going to have that. So we're going to get ourselves, this is ln of 2 plus root 3. I'm dropping the modulus sign here because clearly 2 plus root 3 is positive. So this is the exact answer to the integral. So I'll write that up here for future reference. I'm going to rub this out. This is actually equal to ln of 2 plus root 3. So that's the exact answer. Right, let's have a go at the other parts. We're going to use the trapezium rule with 2 strips to estimate I. First thing we do is we work out h. h is equal to b minus a over n, which in our case is pi by 3, subtract 0 all over 2, which is equal to pi by 6. Okay, now we're going to draw our table. So here's our x values, here's our y values, and here's our trapezium rule. So we're going to have x0 equals 0, x1 equals pi by 6, x2 equals pi by 3. Now y0 is what happens when I put 0 into the function, so sec of 0, which is 1 over cos 0, which is 1. And then y1 is going to be sec of pi by 6. Well, let's just sec of pi by 6 is 1 over cos pi by 6, and cos pi by 6 is root 3 over 2, so 1 over root 3 over 2 is 2 over root 3. Okay, and lastly, when you put pi by 3 in, what would happen if you put pi by 3 in here? Sec of pi by 3 is 1 over cos pi by 3. Cos pi by 3 is a half, so 1 over a half is 2. So you're going to get 2 here. Now the trapezium rule says take x0, take even y0 to be 1, and take yn, y2 to be 2, and double this one here. So we're going to do 2 y1s, which is going to be 4 over root 3. I'm going to add this up. So 1 plus 4 over root 3 plus 2, and we get ourselves here 9 plus 4 root 3 over 3. That's what my calculator says, or your calculator may decimalize it. So therefore, I, an approximation for I, what do we do at the end? We times by a half h, so we do a half times h, which is pi by 6, multiplied by 9 plus 4 root 3 over 3. And that will give us our approximate for I. And we get ourselves 1.389997951. It asked us, I will leave it like that for now because it didn't ask us any more than that. Okay, now just comparing it to the answer for this, I never actually worked out what that was to, as decimalized, that would be ln of 2 plus root 3, which is 1.316957897. And for part B then, our estimate so far is 1.389997951. Okay, so we've done part B. Okay, let's have a go at part C now. Part C is we're going to use 4 strips now, so we'd expect a closer answer than this. So our h is going to be pi by 3 take away 0 all over 4, which is going to be pi by 12. Now we're going to have our x, our y, and our trapezium rule. Now the table is going to be a bit longer now, obviously. So my x0 is going to be equal to 0, and sec of 0 we've said previously is 1. I'm going to have that in my final one. And then we're going to have x1, x2, x3, x4. So x1 is going to be when it's pi by 12. The next one's when it's going to be pi by 6, pi by 12 plus pi by 12. The next one's going to be when it's pi by 6 plus pi by 12, which is going to be pi by 4. And the last one's clearly going to be pi by 4 plus pi by 12, which is obviously going to be pi by 3. Okay, so y1 is going to be sec of pi by 12, okay, which is 1 over cos pi by 12. So we just type in our calculator 1 over cos so type in 1 over cos of pi by 12, and our calculator gives us back the answer here, root 6 minus root 2. And then we're going to type in 1 over cos of pi by 6, and our calculator gives us for that y2 is going to be 2 root 3 over 3. And then we're going to get y3, we're going to type in 1 over cos pi by 4, which we're going to get root 2. And lastly, we're going to type in 1 over cos pi by 3, and we're going to get 2. Now we want the y0 and yn, so we're going to take those as they are, but we're going to double the rest. So this one here, we're going to have 2y1, which is going to be 2 root 6 minus root 2. We're going to have 2y2s, which are going to be 4 root 3 over 3. And we're going to have 2y3s, which are going to be 2 root 2s. Okay, now what we're going to do is we're going to add this up. So we're going to do a total now. We're going to add this up here. So we're going to have 2 plus 1 plus 2 root 6 minus root 2, close brackets, plus 4 root 3 over 3 plus 2 root 2, and you type that in and you're going to get 10.20838.056. So therefore my approximation to I is going to be a half times h, so a half times pi by 12 times by this 10.20838.056. So 10.20838.056 times 0.5 and times pi by 12, and you get yourself 1.336273891. So going up here, you get as an estimate which is closer to the real thing 1.336273891. Okay, so 4 strips gave me a better answer. Okay, last part, let's do part D and be done with it. Okay, so the percentage error using the 2 estimates. So for part D, we should remember percentage error. Percentage error is estimate minus actual over actual times 100. Okay, so for let's say 2 strips, the percentage error is my estimate, which is 1.389999791. Take away 1 point, the actual, this one 1.316957897, all over 1.316957897 times 100. So it's a bit of number crunching here in your calculator, but it's not too hard really, is it? So it's going to be 1.389997991, take away 1.316957897 divided by 1.316957897 times 100. So the percentage error here is going to be equal to 5.55% error. And if we're doing 4 strips now, let's do that in a different colour. The 4 strips percentage error, well, it's going to be equal to my guess, which is 1.336273891. Take away 1.316957897 divided by 1.316957897 times 100. So again, just a bit of number crunching here. You'd expect a lower percentage error. So 1.336273891. Take away 1.316957897 divided by 1.316957897 times by 100, and you're going to get yourself 1.47%, which is a lower percentage error, so it's closer to the integral. So that's that for this video, and that's everything on the trapezium rule. So to finish off with, make sure you read chapter 6, page 101 to 110, and complete exercise 6H, all questions. Thanks for watching.